Today we're going to continue our understanding of nuclear reactions and focus on the energy that's released when a nuclear reaction occurs. These are some of the problems that you had for nuclear decays, nuclear reactions. And the thing to remember is that when this nuclear reaction occurs, this nucleus basically breaks apart or explodes into these products. For example, this lead-210, you can think of this this is called the parent nucleus, and this is called the daughter nucleus, and then the products that are emitted from that. This parent nucleus you can think as a stick of dynamite sitting on the ground. It explodes or decays, and when it decays or explodes, it forms these two particles. But like a stick of dynamite, when it explodes, it has energy. Energy is released, and that energy is released in the form of the kinetic energy of these particles. But where does that energy come from? The energy comes from the loss of mass of this parent nucleus. We're going to see how we can use the loss of mass between the daughter particles and the parent particles, the products and the reactants, and how much mass is lost and how that's converted into the kinetic energy of these particles. Basically, we're going to go through a series of derivations. You don't need to write these derivations down. It's important to go through those derivations to understand where they came from. The main thing is you want to get the results of each of these derivations. I'm also going to throw in another type of nuclear reaction called electron capture, and we'll see how that works. All right, so this is the derivation. There are four different derivations that we're going to go through. And I'm not going to go through each one individually. I'll talk about the alpha one and then maybe a couple other ones specifically. But remember, when we look at the atomic masses of these particles on this table includes the mass of electrons around each of those atoms. And we're only interested in the mass of the atoms themselves. So we have to take into account the electrons. So this is what's happened. This is some nucleus, atomic number Z. And when it goes through an alpha decay, it loses 2 protons and 4 nucleons and forms this alpha particle. Basically what we want to do, we want to take the mass of this reactant and subtract the mass of the products to get the difference in mass. That difference in mass is what's released as a form of energy. And it's released in the form of energy based on this equation. Right? And so let's take a look and see how that works. So this is the mass of the reactant, the parent nuclei, and we're subtracting the mass of those electrons, Z mass of electrons. And because we want the energy, we multiply it by C squared. And so then this is minus the mass of the daughter nucleus, which is X prime, and we have to take into account these 2 extra electrons that are included in that because this mass of electrons stays with this particle. So we subtract those 2 extra electrons. And then this is the mass of the helium nucleus. Again, we subtract the mass of those 2 electrons. But let's see how the electrons cancel out. So over here, we multiply all this out. This is the mass of the 2 electrons. We're going to take this, we're going to expand this out, we're going to expand this out. This is mass of the daughter nucleus minus the electrons. And then this is the mass of the helium particle minus the 2 electrons on the helium particle. We're going to expand this part out, and we get the Z mass electrons minus 2 electrons here. And notice what happens to the mass of electrons. This is Z mass electrons and positive Z mass electrons. Those cancel out. And this value and this value, this is plus, this is negative, those cancel out. We end up getting this equation. We simplify this by taking the C out of there. So these are the mass difference of the particle. This is the starting mass. These are the product masses. And remember, in order to convert mass into energy, which is basically what this equation is, this is the difference in the masses. This is the reactant masses. These are the product masses. We multiply that by 900. I put 931.5 megaelectron volts in your information sheet. It's just 931 because I think it's like 931.45. I round to the nearest tenth. They round to the nearest 1 place. This is the energy of 1 atomic mass unit. So if we use these mass and atomic mass units, that's the energy difference that we get when an alpha decay occurs. Notice we can go through a similar thing and again, this is the final equation that you need to know for an alpha decay. and we do a beta decay, a similar type of thing happens. We take into account the electrons at the beginning and electrons at the end, and notice these electrons cancel out. And notice what we have happen then for that final equation. Simply the mass of the reactant, the parent nuclei, minus the mass of the daughter nuclei times that conversion between energy and atomic mass units. Beta decay is a little more interesting. In beta decay, we have, these are the mass electrons to start with, then it's actually losing an electron, so we cancel it out like this. Then we have to subtract that mass of the electron that is from the nucleus. And so we have this value here. Now look how they cancel out mathematically. Notice this cancels this, but this is minus mass electron, and this is minus mass electron, so we get -2 mass electrons there. So this is the equation. We have to take the mass of the product minus the mass of, the mass of the reactant minus the mass of the product. And we also have to subtract the mass of 2 electrons. Of course, times the conversion between energy and atomic mass units. Again, this is the equation you need to know for beta positive decay. And the electron capture is kind of interesting. Electron capture occurs when a nucleus actually has too few neutrons, and what happens is this nucleus has such a strong attraction for the inner electrons of the atom itself that actually captures one of its inner electrons into the nucleus and causes a proton to turn into a neutron. So this actually reduces the number of protons and increases the number of neutrons. So this has too few neutrons in that nucleus. So this proton captured electron turns into a neutron and a neutrino. Again, if we look at this reaction taking into account the electrons like we've done before, notice how these electrons cancel. This is -2 mass electrons, +2 mass electrons, positive mass electron, minus mass electrons. So those electrons all cancel out. We end up getting this equation. Again, this is this similar equation as the beta decay, which is simply the mass of the products minus the mass of the reactants, and then the conversion to energy. So this is the equation you need to know for electron capture. Now, let's take a look at an example problem, how we can do this. And on Power School, you have 2 documents you need to download to the Notability. One of them is alpha decay, and the other one is a beta decay worksheet. And we're going to go through one example of an alpha decay problem. And at the top here, these are just reactions that you need to write. You should know how to do this. Write the nuclear reaction for an alpha decay for both of those. But we're going to come down here to find out the energy that is released for this decay process. Basically, write the following nuclear reactions for an alpha decay and calculate the maximum kinetic energy of the alpha particle emitted. Again, what happens when these particles break apart, if I can find my document here, is it forms, there's an alpha decay. So this nuclei here breaks apart into 2 particles. Depending on how it breaks apart and how it's oriented, it's moving, those types of things, some of the kinetic energy that this produces when it explodes, because the mass is converted to energy, some of that kinetic energy is in the form of the motion of the alpha particle, some of the kinetic energy is the motion of the helium particle. Now there can be cases when almost all the kinetic energy is given to the alpha particle and none to the mercury, or there can be cases when some of it is given to the alpha particle and some is given to the mercury. So in this problem, what we have, we're assuming that all that energy is converted to kinetic energy of the alpha particle. So let's take a look at this problem. So this reaction is going to produce lead 82 for the atomic number and 206 for the atomic mass number plus the alpha particle. I'm going to write the alpha particle as helium 42 like this. Again, this equation, the energy that's produced when this change of mass occurs in the nuclear reaction, is going to be the mass of the parent nuclei minus the mass of the daughter nuclei. This is the parent, this is the daughter, minus the mass of the alpha particle, and of course times 931.5 megaelectron volts per atomic mass unit. This is from E equals mc squared. Again, if you want to just use 931, I'm using 931.5, it doesn't matter, the process is the same. So we're going to get this Q is going to be equal to mass of the parent, which is the mass of this polonium-210. Again, we look it up on this table to get the mass, which again includes the mass of electrons. This is going to be 209.982416 atomic mass units, minus the mass of the daughter, which is lead-206, minus 205.974449 atomic mass units, then the mass of the alpha particle, which is 4.002603 atomic mass units, and all that times 931.5 megaelectron volts per atomic mass unit. You do that calculation, we get this Q is going to be equal to 0.005364 atomic mass units times 931.5 megaelectron volts per atomic mass unit. Did I write that correctly? That's a per atomic mass unit in parentheses. We end up getting it's 4.996 megaelectron volts of energy released, and this, if it says the maximum amount of kinetic energy of the alpha particle, that means all of that energy is converted to the kinetic energy of the alpha particle. Now, if it's set up here that 20% of it was converted to kinetic energy alpha particle and 80% kinetic energy of the lead-206, then we could split that up and determine the kinetic energies of each. And of course, if we know the mass of the alpha particle, which we know, and that's the kinetic energy of it, we could also determine the speed that the alpha particle is traveling because of the equation kinetic energy equals 1/2 mv squared. Just a little aside there. So what you need to do now, you need to finish this document, download it to Notability, and do the problems, and finish this document for the beta decay. Download this document to Notability and finish all the aspects of it. Notice this one has both beta negative and beta positive decay.